The universe we believed extended 14 billion light years in every direction actually measures 93 billion light years across. The James Webb Space Telescope aimed its instruments at what appeared to be an empty void and uncovered nearly 800,000 galaxies concealed in the cosmic darkness. Galaxies that ignited into existence when the universe was merely 300 million years young. Black holes containing masses billions of times greater than theoretical limits should allow. Cosmic structures extending across tens of millions of light years that formed impossibly fast. Everything humanity understood about the universe's dimensions was fundamentally incomplete. The cosmos is vastly larger, more complex, and stranger than we ever imagined. Light requires time to traverse space. When you observe an object 1 mile distant, you're seeing it as it existed 5 microseconds in the past. Glance at the moon, and you witness its appearance from 8 seconds ago. Focus on the nearest stellar neighbor, and you're receiving light that departed over 4 years before this moment. This represents established scientific fact. Every photon traveling through the void carries a preserved record of the instant it began its journey. The James Webb Space Telescope maintains its position 1 million miles from our planet, continuously observing the darkness beyond. Its primary mirror spans 21 feet in diameter, layered with gold to capture infrared radiation. Infrared represents what remains after visible light undergoes stretching due to universal expansion. Consider a siren passing you on a highway. The pitch drops lower as the distance between you increases. Light experiences an identical phenomenon across cosmic distances. Webb isn't merely observing distant locations. It's peering backward through time itself. The most remote galaxy it has identified emitted its light 13.5 billion years ago. This means we're observing this galaxy exactly as it appeared when the universe had existed for only 290 million years. For perspective, if you compress the universe's entire age into a single calendar year, this galaxy would have formed on January 2nd. Here's what makes this extraordinary beyond measure. The light traveling toward us has been moving through space for nearly the complete duration of existence. When that light commenced its journey, Earth didn't exist. Our sun hadn't formed. The Milky Way remained in the process of assembling itself from primordial cosmic gas. Dinosaurs, human civilization, everything we recognize emerged and disappeared while these photons crossed the void. Every image Webb captures functions as a fossil, a preserved instant frozen in electromagnetic radiation. The telescope collected photons for nearly 10 hours to capture one ancient galaxy. 10 hours of gathering light that has been in transit for 13.5 billion years. The patience this requires staggers the imagination. Scientists employed an instrument called a spectrograph to verify the distance. This device separates light into its component wavelengths, like a prism creating a rainbow. Specific patterns within that spectrum reveal how rapidly the universe has been expanding since the light departed its source. The farther away an object resides, the more its light has been stretched during transit. This galaxy displayed a redshift of 14.32, representing the highest value ever recorded for a confirmed galaxy. What this signifies for our understanding is profound. We're not simply observing distant objects. We're witnessing the universe's infancy. We're seeing the first structures that would eventually lead to everything we know today. Every star, every planet, every atom comprising your physical form can trace its lineage back to these primordial moments. But distance creates problems scientists never anticipated. The galaxy carries a designation that resembles a serial number: JADESGSZ140. Scientists identified it in October 2023, then spent months questioning what their instruments revealed. It appeared too luminous, too expansive, too developed for something that shouldn't exist in this cosmic era. When astronomers directed Webb's spectrograph at this galaxy in January 2024, they verified their initial observations. The object sits 13.5 billion light-years away, having formed just 290 million years after the Big Bang. This places it within an epoch called Cosmic Dawn, when the first stars were theoretically beginning to flicker into existence. Emphasis on theoretically. Here's the fundamental problem. This galaxy measures over 1,600 light-years across. That's minuscule compared to modern galaxies, yet enormous for its age. It contains several 100 million times the mass of our Sun, all concentrated within young stellar populations. The light originates from stars, confirmed through spectral analysis. Newly ignited stars radiating intense ultraviolet radiation. Theoretical models predicted early galaxies would manifest as small, dim, simple collections of perhaps a few million stars at most. The universe, at 290 million years old, shouldn't have possessed sufficient time to construct anything substantial. Gravity operates slowly. Gas collapses gradually. Stars require millions of years to form. Dark matter halos need extended periods to accumulate enough material to seed galaxy formation. Yet, there it exists, bright enough that Webb could detect it, even if it were 10 times fainter. That detail disturbs astronomers profoundly, because it suggests this galaxy isn't an isolated anomaly. If one exists at this distance, dozens more probably hide in regions Webb hasn't surveyed yet. The team discovered a second galaxy nearly as distant, labeled JADESGSZ141, two record-breaking galaxies within the same field of view, both displaying properties that contradict standard cosmological models, both producing starlight at rates that should be physically impossible. What makes researchers especially troubled is the chemical composition. Spectral lines revealed not just hydrogen and helium, but heavier elements: carbon, oxygen, nitrogen. These atoms only form inside stars, then disperse through space when those stars explode as supernovae. This means an earlier generation of stars must have already lived and died before this galaxy formed. The timeline keeps being pushed backward into increasingly impossible territory. One astronomer described discovering this galaxy as analogous to excavating a smartphone among ancient Roman ruins. The technology appears too advanced for its era, the structure too sophisticated, the luminosity too intense. This discovery forced scientists to extend humanity's view into the cosmic past by 40% during Webb's first 18 months of operation. 40% deeper into time than we'd ever seen before. The question nobody can adequately answer: if galaxies this massive existed this early, what else are we missing in the darkness? Here's where the universe stops making intuitive sense. Light travels at 186,000 miles per second. Nothing moves faster through space. This has been confirmed by every measurement we've ever conducted. In 1 year, light covers approximately 6 trillion miles. Multiply that by the universe's age of 13.8 billion years, and you derive how far light could travel since the Big Bang. The answer should be 13.8 billion light years. Simple mathematics. Except that calculation is completely wrong. The actual edge of the observable universe sits 46.5 billion light-years away in every direction. The total diameter measures 93 billion light-years across. We inhabit a sphere of space nearly 7 times wider than the distance light could possibly traverse in the universe's lifetime. This isn't a measurement error. It's expansion. Space itself is stretching. Imagine drawing dots on a balloon surface, then inflating it. The dots separate, even though they're not traveling across the balloon's material. The surface between them is growing. Space functions identically. Galaxies aren't flying through space. Space is carrying them apart. When a distant galaxy emitted light 13.5 billion years ago, it was significantly closer to us than it is presently. That galaxy has been receding from us the entire duration its light traveled toward us. By the time that ancient light reaches our telescopes, the galaxy that emitted it has drifted to a current distance of 46 billion light-years. Think of it like running on a treadmill towards someone standing ahead of you. While you run forward, the treadmill pulls you backward. You might eventually reach them, but they'll be farther away than when you started running. Light does the same thing, fighting against cosmic expansion. Here's what makes this deeply strange. Regions of the universe exist beyond 46.5 billion light-years. We know they're there because space extends infinitely in all directions. The observable universe represents only the portion where light has had time to reach us. Beyond that boundary, galaxies shine and stars explode and planets orbit, we simply can't see them. We never will. The expansion rate is accelerating, confirmed by observations of distant supernovae. This acceleration is caused by something called dark energy, which comprises 68% of everything that exists. Dark energy's density remains constant as space expands, meaning its total quantity increases as the universe grows larger. What this means for cosmic structure is profound. The universe is simultaneously finite in what we can observe and infinite in what actually exists. Every second, the edge of what we can see grows larger, but space itself grows faster. Distant galaxies are disappearing beyond our reach. And stranger still, the rate of expansion appears different depending on where we look. Webb examined a patch of sky slightly larger than 3 full moons for 250 hours. The region is called the Cosmos Webb Field. When Hubble examined this identical area, it identified roughly 10,000 galaxies. Scientists believed that represented a complete census. They were wrong by a factor of 80. The final Webb image contains 797,942 galaxies, nearly 800,000 distinct collections of stars, each containing billions or trillions of stellar masses. The photograph required combining more than 10,000 individual exposures, carefully aligned and corrected for observational errors. To understand the scale, picture printing the famous Hubble ultra-deep field on a standard sheet of paper. The Webb image would need to be printed 13 feet tall by 13 feet wide at equivalent detail, a wall-sized mural of cosmic history. Every single galaxy in this image tells a unique story. Some formed 12 billion years ago when the universe was young and chaotic. Others took shape relatively recently, just a few billion years past. The catalog includes measurements for each galaxy's distance, brightness, mass, and star formation rate. Scientists can now track how galaxies evolved across 98% of cosmic time. What makes this image revolutionary isn't just the quantity of galaxies, it's their distribution. The galaxies aren't scattered randomly across space. They cluster along invisible threads. They congregate at intersections. They avoid certain regions entirely. The pattern reveals the cosmic web, a large-scale structure of dark matter filaments connecting every major mass concentration in the universe. Webb's infrared vision pierced through cosmic dust that had concealed entire populations of galaxies from previous surveys. What appeared empty in visible light blazes with activity in infrared. Dusty regions where new stars form. Ancient galaxies whose light has been stretched into wavelengths human eyes cannot detect. Objects Hubble literally couldn't see, regardless of how long it observed. The team spent years developing technology to measure properties of 800,000 galaxies simultaneously. Photometry to gauge brightness. Morphology to classify shapes. Redshift calculations to determine distances. Physical parameters to estimate masses and ages. The catalog represents one of the highest quality datasets in astronomy. Scientists released everything to the public. The images, the measurements, the catalog, an interactive viewer where anyone can search for specific objects or explore random patches of deep space. This democratization of data means researchers worldwide can mine the information for discoveries. Before Webb launched, astronomers predicted they would find approximately 10 times fewer galaxies at extreme distances. They estimated galaxies forming within the first 500 million years would be incredibly rare, perhaps a few dozen in a survey this size. The actual count exceeded predictions by a factor of 10. Hundreds of extremely distant galaxies crowded into a cosmic era that should have been nearly empty. Something about early galaxy formation is fundamentally wrong in our theoretical models. The Big Bang occurred 13.8 billion years ago, confirmed by multiple independent measurements. Afterward, the universe was smooth, nearly uniform. Tiny density fluctuations existed, but matter was distributed almost evenly throughout space. Gravity amplifies these fluctuations over time, pulling matter into concentrations that eventually become stars and galaxies. This process should be slow, predictable, gradual. Current models estimate how quickly the first structures could form. Gas needs time to cool enough for gravity to compress it. Dark matter halos need to accumulate sufficient mass to attract ordinary matter. Stars need to ignite and produce the heavy elements that seed future star formation. Each step requires millions of years. The mathematics adds up to a clear prediction about how many galaxies should exist at any given cosmic age. Webb found 10 times more galaxies in the early universe than those predictions allowed. 10 times. Researchers checked the instruments, verified the measurements, examined the data for systematic errors. Everything confirmed the same impossible result. Within the first 500 million years after the Big Bang, the cosmos was teeming with galaxies. Bright ones, massive ones, galaxies containing billions of stellar masses worth of material. The universe was producing too much light too early. It had only 400 million years to form structures containing 1 billion times the mass of our sun. We don't know how to make that happen with current physics, with current understanding of how matter behaves. One explanation suggests that stars formed more efficiently in the early universe. Perhaps gas collapsed faster because the cosmos was denser. Perhaps gravitational collapse worked differently when space was more compressed. Perhaps environmental conditions allowed star formation to proceed at rates impossible in the modern universe. But this is speculation, not confirmed theory. The observations are real. The explanations remain uncertain. Another possibility involves dark matter. Different models of dark matter predict different abundances of dark matter halos in the early universe. If dark matter behaves differently than the standard model assumes, it could create conditions that accelerate galaxy formation. Measurements from Webb might help distinguish between competing dark matter theories. What troubles astronomers most is the consistency of the surprise. It's not one anomalous galaxy. It's hundreds across multiple surveys in different regions of sky, using different instruments. Every deep field Webb examines reveals the same pattern: far more galaxies than should exist. The implications reach beyond simple number counts. If galaxies form this abundantly, they must have influenced their surroundings earlier than expected. They would have started reionizing the universe sooner. They would have enriched space with heavy elements faster. They would have seeded the formation of larger structures earlier. The entire timeline of cosmic evolution might need revision. Every textbook chapter on the early universe might be incomplete, and some of those early galaxies are so massive they border on impossible. Astronomers discovered galaxies in the infant universe that weigh 100 times more than theory permits. These objects appeared so impossible that researchers initially called them universe breakers, because their existence seemed to violate the laws of cosmology. The problem comes down to time. Building a massive galaxy requires accumulating enormous amounts of matter. Dark matter must collapse into a halo first. Then, ordinary matter falls into that halo. Then gas cools and fragments. Then, stars form. Then those stars live out their lives and die. Then the heavy elements they produce seed the next generation of stars. This cycle repeats over and over as the galaxy grows. Each step has a minimum duration determined by physics. You can't compress gas faster than the speed of sound without creating shock waves that heat it back up. You can't form stars instantly. You can't skip the waiting period while stellar evolution proceeds. The standard model of cosmology calculates exactly how massive a galaxy can become at any given age. Some early galaxies exceeded those limits by factors of 10 to 100. They appeared to contain more stars than should be possible given the time available. Their brightness suggested stellar populations too large for the cosmic era in which they formed. Scientists scrambled to explain this phenomenon. Perhaps the galaxies weren't as massive as they appeared. Perhaps bright active galactic nuclei made them look bigger. Perhaps supermassive black holes at their centers contributed significant light, making the galaxy seem more luminous than the stars alone would produce. Recent analysis suggests this explanation is partially correct, though not completely. Some of the universe breakers do harbor extremely bright black holes that inflated their apparent mass. When astronomers account for black hole contributions and reanalyze the data, the galaxies shrink to more reasonable sizes. They're still massive for their age, but they no longer break the universe. However, even after corrections, roughly twice as many massive galaxies exist in the early universe as models predict. The discrepancy has narrowed from a factor of 100 to a factor of 2. But the problem hasn't disappeared. Something about early galaxy formation remains unexplained. One team compared Webb observations to Hubble's census of galaxies at similar distances. Hubble had been observing for decades, building a representative sample of what existed in various cosmic epochs. If the standard model was correct, Webb and Hubble should see similar distributions of galaxy masses. Any increase in Webb's counts should come from detecting fainter galaxies Hubble missed. Instead, Webb found far more bright, massive galaxies than Hubble's data suggested should exist. This inconsistency points to either environmental differences in the early universe or gaps in our understanding of how efficiently matter converts into stars. The research continues. Each new observation refines the puzzle. Each measurement narrows the range of possible explanations. What remains certain is that massive structures appeared earlier than expected, and at the centers of some of these galaxies lurk monsters even more perplexing. A supermassive black hole sits at the heart of galaxy GNZ11, one of the most distant galaxies ever observed. This black hole existed when the universe was only 430 million years old. Its mass equals millions or possibly billions of times the mass of our Sun. That should be impossible. Black holes form when massive stars collapse at the end of their lives. A star needs to be at least 20 times more massive than our own to create a black hole when it dies. The resulting black hole typically weighs 10 to 100 times what our Sun weighs. From there, it can grow by consuming gas, dust, and other stars. But this process takes time, billions of years to reach supermassive status through gradual accumulation. 430 million years isn't enough time. Even if a black hole formed immediately after the Big Bang and consumed material continuously at the maximum possible rate, it couldn't grow to billions of stellar masses by this early date. The physics of matter falling into black holes imposes strict limits on growth speed. Yet there it was. Webb detected extremely dense gas surrounding the black hole, a signature of rapid accretion. The black hole was actively feeding, pulling matter inward at tremendous rates. Spectral analysis revealed patterns that only appear near supermassive black holes consuming gas. This galaxy isn't unique. Webb has discovered multiple supermassive black holes in the early universe. Some appear even more massive than expected for their cosmic age. Each discovery deepens the mystery of how these objects grew so large so quickly. Several theories attempt to explain this phenomenon. One possibility involves dark stars, theoretical objects powered by dark matter annihilation rather than nuclear fusion. These stars could grow to millions of times the mass of our Sun before collapsing directly into massive black holes, providing a head start on growth. Another theory suggests that in the dense early universe, gas clouds could collapse directly into massive black holes without forming stars first. If conditions were right, a cloud containing 100,000 stellar masses might compress straight into a black hole of equivalent mass. This has never been observed, but mathematical models show it's theoretically possible. A third explanation involves collisions. If smaller black holes merged frequently in the crowded early universe, they could build up mass faster than accretion alone allows. Gravitational wave detectors have confirmed that black hole mergers occur. Perhaps they happened far more often in the past. What makes these black holes especially important is their role in galaxy evolution. Black holes don't just sit passively at galactic centers. They blast out enormous amounts of energy as matter spirals inward. This radiation heats surrounding gas and can either trigger star formation or shut it down completely. Supermassive black holes help regulate how galaxies grow. Finding them so early means they influenced cosmic evolution from nearly the beginning. Their presence could explain some of the unexpected galaxy properties Webb keeps discovering. But before these black holes existed, something even stranger might have burned in the primordial darkness. Scientists detected something peculiar in the spectrum of galaxy GSZ12. The light contained an extreme imbalance of nitrogen compared to oxygen. The ratio measured 0.46, which is bizarre for any normal stellar population. Stars don't naturally produce that chemical signature. Stellar explosions don't create it either. But theoretical models predicted exactly this signature, from a type of star never observed, primordial monster stars thousands of times more massive than our own. These theoretical giants would have formed in the very early universe from clouds of pure hydrogen and helium. No heavy elements existed yet to contaminate the gas. The first generation of stars, called Population 3, consisted entirely of the lightest atoms. Without heavy elements to help cool the gas, these clouds collapsed into much more massive stars than formed today. A monster star might weigh 1,000 to 10,000 times what our sun weighs. It would burn incredibly hot. Its core would fuse helium into carbon at ferocious rates. The carbon would then capture additional helium nuclei through a process called the carbon-nitrogen-oxygen cycle, producing vast quantities of nitrogen. These stars would burn brilliantly for perhaps only a few million years before exhausting their fuel. When they died, they wouldn't explode like normal supernovae. They would collapse directly into massive black holes. But during their brief lives, they would spew nitrogen-rich material into space through powerful stellar winds. That material is what Webb detected in GSZ-12, the chemical fingerprint of monster stars that lived and died billions of years ago. The nitrogen they produced remained in the galaxy, mixed with later generations of normal stars, creating the unusual spectrum astronomers observed. This discovery provides the first clear evidence that Population 3 monster stars actually existed. For decades, they remained purely theoretical. Mathematical models showed they should form, but nobody had ever detected their chemical signatures in real galaxies. Webb changed that. The implications reach far beyond confirming a prediction. Monster stars help solve the supermassive black hole problem. If stars this massive collapse into black holes, weighing thousands or tens of thousands of stellar masses, those black holes would have a huge head start on growth. They could reach supermassive status much faster than black holes formed from normal stars. Monster stars also contributed to reionization, the period when the first sources of light began ionizing the hydrogen gas that filled space. Their intense ultraviolet radiation would have stripped electrons from atoms across vast regions, making the universe transparent to light. This process transformed the cosmos from an opaque fog into the clear medium we observe today. Additionally, these stars produced the first heavy elements. Every atom of carbon, oxygen, and nitrogen in the early universe came from stellar interiors. Monster stars forged these elements faster and in greater quantities than normal stars could. They seeded the formation of subsequent star generations that could form planets and eventually life. The universe's largest stars burned at the beginning, not now. They were brief but essential architects of everything that followed. Yet even these giants were just individual objects. The universe's true scale reveals itself in its largest structures. The universe isn't distributed evenly. Galaxies cluster along threads of dark matter that stretch tens of millions to hundreds of millions of light years across space. These filaments connect at massive intersections where thousands of galaxies accumulate. Between the threads lie voids, vast empty regions where almost nothing exists. This pattern is called the cosmic web. It represents the largest structure in the universe. Every major concentration of matter connects to it. Every galaxy lives somewhere on its threads. The web pervades the entire observable cosmos, integrating all gravitationally bound structures into one interconnected network. The web formed from tiny density fluctuations in the early universe. Regions that were slightly denser than average had slightly more gravity. They pulled in more matter, which increased their gravity further. The process amplified over billions of years, creating denser and denser regions connected by streams of infalling material. Think of it like water flowing downhill into valleys. The valleys represent regions of higher dark matter density. The streams represent filaments where matter flows from one concentration to another. Over cosmic time, these streams become highways of galaxies traveling along gravitational corridors. Dark matter provides the scaffolding. It comprises 85% of all matter in the universe, confirmed by gravitational effects on visible matter. Dark matter doesn't emit light or interact with electromagnetic radiation. We detect it only through its gravity. Where dark matter concentrates, normal matter follows. Scientists map the cosmic web by surveying millions of galaxies and measuring their positions in three-dimensional space. Patterns emerged. Galaxies line up along specific directions. They cluster at nodes where multiple filaments intersect. They avoid regions between filaments. The distribution reveals the underlying dark matter structure. The local group, which includes our galaxy and Andromeda, sits on a filament connecting the Fornax cluster to the Virgo cluster. This filament stretches approximately 110 million light-years across. Light from some parts of our local structure departed when dinosaurs walked on Earth. The largest concentrations occur where filaments meet. These intersections become galaxy clusters, the most massive gravitationally bound objects in existence. A typical cluster might contain 100 to 1,000 galaxies, with a total mass of 100,000 billion stellar masses. They represent the high-density nodes of the cosmic web. Material flows along filaments toward these clusters. Galaxies that started out isolated drift along the threads and eventually join cluster populations. As they travel, they interact with other galaxies. Collisions occur, mergers happen, gas gets stripped away by the hot plasma filling space between galaxies. These environmental effects transform spiral galaxies into elliptical ones. Recent observations detected dark matter directly on filaments for the first time. Using gravitational lensing, scientists observed how light from distant objects bent around invisible mass concentrations along cosmic web threads. The measurements confirmed that dark matter really does line the filaments, not just concentrate at nodes. For the first time, scientists detected dark matter hanging from the cosmic web's terminal segments, the thin threads connecting clusters to individual galaxies. This confirmed theoretical predictions about how the largest structure organizes space. But Webb revealed something even more extreme: specific concentrations that challenge the limits of what the web can build. Astronomers using Webb data discovered a massive chain of at least 20 closely packed galaxies. They call it the cosmic vine. It swoops through space in a bow shape stretching more than 13 million light-years long and approximately 650,000 light-years wide. For comparison, our entire galaxy measures only 100,000 light-years across. All 20 galaxies showed a redshift of roughly 3.44, meaning their light traveled between 11 and 12 billion years to reach us. They existed when the universe was only a few billion years old. The vine formed during an era when such large structures shouldn't have had time to assemble. What makes the cosmic vine remarkable is its size compared to other galaxy groups at similar distances. It's significantly larger than anything else discovered at this cosmic epoch. The structure appears to be in the process of becoming a galaxy cluster, one of the universe's most massive formations. Current mass estimates place the vine at approximately 260 billion stellar masses. That's already enormous. But it's still growing. Galaxies continue to drift along the filament, drawn by the combined gravity of the structure. Eventually, over the next several billion years, these galaxies will merge into a unified cluster. What puzzles researchers is the state of the two largest galaxies in the vine. When scientists analyzed the wavelengths of light these galaxies emitted, they found that star formation had almost completely stopped. The galaxies are classified as quiescent, meaning they're no longer actively producing new stars. This is unusual for the early universe. Most galaxies at this distance are still forming stars vigorously. Finding large galaxies that have already used up their gas reserves suggests something dramatic occurred. One possibility is that these galaxies resulted from recent mergers. When galaxies collide, they can trigger massive bursts of star formation that consume available gas in a relatively short period. The collision would heat the gas to extremely high temperatures. Hot gas doesn't collapse easily to form stars. It can also be expelled from the galaxy entirely by the energy released during the merger. This would leave behind a galaxy full of existing stars, but depleted of the raw material needed to build new ones. Another explanation involves the environment. Galaxies in dense structures experience different conditions than isolated galaxies. They pass through hot plasma, filling the space between galaxies. This plasma can strip away their gas through a process called ram pressure stripping. Imagine extending your hand out of a car window at highway speeds. The air resistance pushes your hand backward. Gas in galaxies experiences similar forces when moving through the hot medium between galaxies. The cosmic vine represents just one example of unexpected large-scale structure in the early universe. Webb keeps finding massive concentrations that formed faster than models predict. Each discovery adds evidence that something about early structure formation proceeds more efficiently than standard theory allows. These enormous structures don't exist in isolation. They're part of a much larger population of galaxy groups that Webb has cataloged across cosmic time. A team of astronomers compiled the largest and deepest sample of galaxy groups ever observed. They detected 1,678 galaxy groups and protoclusters spanning from 12 billion years ago to approximately 1 billion years ago. This catalog maps cosmic family trees from near the beginning. Each galaxy group represents a collection of galaxies held together by gravity. They're smaller than massive clusters, but larger than individual galaxies. Think of them as neighborhoods in the cosmic web. Distinct communities connected by the larger structure, but maintaining their own local gravitational identity. What makes this catalog revolutionary is its depth. Previous surveys could only glimpse parts of this evolutionary sequence. They might catch groups at one cosmic epoch or another, but they couldn't trace continuous development across billions of years. Webb changed that. Its infrared sensitivity allows detection of galaxies 1 billion times, fainter than what human eyes can see. The catalog reveals how galaxy groups evolve over time. In the early universe, groups appear chaotic. Galaxies show irregular shapes. Star formation proceeds vigorously. The structures are loose, still assembling, not yet settled into stable configurations. As time progresses, the groups become more organized. Galaxies develop symmetrical shapes like spirals and ellipses. Star formation slows down, a process called quenching. The groups grow more compact as gravity pulls members closer together. Eventually, many groups merge into larger clusters. This evolution reflects broader processes, shaping cosmic structure. Dark matter halos accumulate over time. Small halos merge into larger ones. Gas heats up as it falls into these halos. Supermassive black holes at galactic centers blast energy into surrounding space. All these effects combine to transform the properties of galaxies and the groups they inhabit. Scientists can now track individual galaxy populations through multiple evolutionary stages. They identify galaxies at one distance, then look for similar galaxies at other distances to see how that population changed. This creates a narrative of cosmic history, showing how different types of galaxies emerged and evolved. The catalog also reveals environmental effects. Galaxies in dense groups behave differently than isolated field galaxies. Group members experience more frequent interactions. They collide more often. Their gas gets heated by the hot plasma filling space between them. These environmental factors accelerate evolution, transforming active star-forming galaxies into quiescent ones faster than would happen in isolation. One particularly striking finding involves the transition from chaotic to organized. The shift occurs fairly rapidly in cosmic terms, over just a few billion years. Early groups show high star formation rates and irregular morphologies. Later groups show low star formation and regular shapes. The transformation coincides with the era when dark matter accumulation shifted from rapid growth to slower consolidation. This catalog provides observational evidence for theories about how structure forms in the universe. It confirms predictions about halo assembly. It validates models of environmental quenching. It demonstrates how the cosmic web organizes matter on the largest scales. Yet even with nearly 1,700 groups cataloged, vast regions of space contain nothing at all. Between the filaments of the cosmic web stretch enormous empty regions called voids. These spaces contain almost no galaxies, almost no stars, almost no matter of any kind. They extend for hundreds of millions of light years in every direction, representing the largest continuous volumes of emptiness in the universe. The voids aren't completely empty. A few small galaxies drift through them, isolated and alone. Sparse filaments of dark matter thread through the edges. But compared to the dense regions where galaxy clusters form, voids contain less than 10% of the average matter density of space. Imagine standing in the middle of a void. Look in any direction, and you would see darkness extending for tens of millions of light years before encountering the nearest galaxy. The void would appear as a cosmic desert, an immense region where structure formation failed to occur. Voids form through a process opposite to how clusters form. Regions that started slightly less dense than average had slightly less gravity. Matter flowed out of these regions toward denser areas. This decreased their density further. The process continued for billions of years, creating vast underdense regions while concentrating matter along the boundaries. These boundaries are where filaments exist. Matter drains from voids and accumulates on the walls separating them. Over time, voids grow larger as more material evacuates toward the edges. The cosmic web evolves by expanding voids and compressing filaments, creating an increasingly structured pattern. The largest known void stretches approximately 1 billion light-years across. That's roughly 1% of the observable universe's diameter. Light takes 1 billion years to cross it. If you started at one edge and traveled at the speed of light, you would spend 1 billion years crossing nothing but empty space before reaching the other side. Scientists study voids because they provide clean laboratories for understanding cosmic expansion and dark energy. In dense regions, local gravitational effects complicate measurements. Galaxies move under the combined influence of large-scale expansion and local attraction. In voids, local effects are minimal. Galaxies move primarily under the influence of cosmic expansion, making them ideal tracers of how fast the universe is expanding. Void statistics also test cosmological models. The number, size, and distribution of voids depends sensitively on dark matter properties and the initial conditions after the Big Bang. Observing more or fewer voids than predicted would indicate problems with standard theory. So far, void counts match predictions, providing evidence that current models capture the broad outlines of structure formation correctly. What makes voids slightly unsettling is their extremity. The universe could have distributed matter more evenly. Instead, it created these vast, empty regions and concentrated almost everything into thin threads and dense nodes. The contrast emphasizes how gravity organizes space, pulling matter together and leaving enormous gaps. Within those gaps, any civilization that arose would see a very different night sky than we do. They would observe far fewer galaxies. Their view of the cosmos would be limited. They might conclude that the universe contains less than it actually does. Meanwhile, the light traveling through both voids and filaments undergoes a transformation that reveals just how far it has come. Every wavelength of light the most distant galaxies emit gets stretched by the expansion of space. Ultraviolet light becomes visible light. Visible light becomes infrared. Infrared stretches into far infrared and beyond. By the time these ancient photons reach our telescopes, their wavelengths have expanded by a factor of 14 to 16 times their original length. This effect is called redshift. The term comes from the fact that stretching wavelengths moves light toward the red end of the spectrum. Blue light shifts to red. Red shifts to infrared. The farther a galaxy sits, the more its light has stretched during transit, and the higher its redshift value. Scientists measure redshift using spectroscopy. Specific atoms emit light at precise wavelengths. Hydrogen produces a characteristic line at 121.6 nanometers in the ultraviolet. When astronomers observed this line shifted to 1,823 nanometers in the infrared, they know the light has been stretched by a factor of 15. This indicates a redshift value around 14. That factor of 15 tells us how much the universe has expanded since the light was emitted. When a galaxy with redshift 14 emitted its light, the universe was 15 times smaller than it is today. All distances were 15 times shorter. All wavelengths were 15 times compressed. Space itself has grown 15-fold since those photons began their journey. Here's where this becomes visually dramatic. The galaxy emitted ultraviolet and blue light from hot young stars. We see none of that in its original form. Every ultraviolet photon has shifted into near-infrared wavelengths between 1 and 3 microns. Every visible photon has stretched to mid-infrared between 3 and 10 microns. The entire spectrum has slid beyond what human eyes can detect. This is why Webb uses infrared detectors. The telescope was specifically designed to observe light from the most distant galaxies, knowing that light would arrive in infrared wavelengths. Previous telescopes, like Hubble, operated primarily in visible and ultraviolet light. They could detect some infrared, but not at the sensitivity needed to see faint, high redshift galaxies. Webb's instruments cover wavelengths from 0.6 microns to 28 microns. This range captures redshifted light from galaxies at virtually any distance in the observable universe. The near-infrared camera operates from 0.6 to 5 microns. The mid-infrared instrument covers 5 to 28 microns. Together, they see light that has been stretched by factors ranging from 2 to more than 20. The redshift also affects brightness. Stretching wavelengths spreads the energy across a broader spectrum, making objects appear dimmer. Additionally, the expansion of space decreases the rate at which photons arrive. Both effects combine to make high redshift galaxies incredibly faint, despite being intrinsically luminous. Webb overcame this through sheer sensitivity. Its large mirror collects more light than any previous space telescope. Its instruments detect incredibly faint signals. Its position at the second Lagrange point 1 million miles from Earth eliminates interference from our planet's heat and light. All these factors allow it to capture photons that have been traveling for 13 billion years. But even as Webb confirms the extreme stretching of light, it has revealed a deeper problem with how we understand expansion itself. The universe is expanding. This is confirmed fact. But when scientists measure how fast it's expanding, they get different answers depending on which method they use. This discrepancy is called the Hubble tension, and it represents one of the most significant mysteries in modern cosmology. One method looks at the early universe. Scientists measure the cosmic microwave background, the faint radiation left over from the Big Bang. This radiation shows a pattern of hot and cold spots that reveals the universe's properties 13.8 billion years ago. From that pattern, they can calculate how fast the universe should be expanding today. The answer comes out to approximately 67 kilometers per second per megaparsec. The other method looks at the nearby universe. Astronomers measure distances to galaxies using objects called Cepheid variable stars and type Ia supernovae. Both serve as standard candles whose intrinsic brightness is known. By comparing how bright they appear to how bright they actually are, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate. This method yields approximately 73 kilometers per second per megaparsec. The gap might seem small, just 6 kilometers per second per megaparsec, but this difference is statistically significant. Both measurements have been verified repeatedly using independent datasets. The cosmic microwave background measurements come from multiple satellites and ground-based telescopes. The nearby universe measurements come from Hubble observations spanning decades. Webb has now confirmed Hubble's measurements using the largest sample of Webb data collected over its first 2 years in space. The team used 3 different methods to measure distances to galaxies that hosted supernovae. All 3 methods agreed with each other, and with Hubble's earlier results. Webb's measurements ruled out the possibility that Hubble made a systematic error, so the tension remains. The early universe predicts one expansion rate. The late universe measures another. These cannot both be correct if our understanding of how the universe evolves is accurate. Several possible explanations exist. Maybe dark energy behaves differently than current models assume. Instead of remaining constant over time, perhaps its strength has changed as the universe aged. This would cause the expansion rate to differ between early and late epochs. Maybe there's some unknown physics affecting how light travels through space. Perhaps interactions with dark matter or other fields modify photon energies in ways we haven't accounted for. This could bias measurements in one direction or another. Maybe our measurements contain unrecognized errors. Perhaps some subtle systematic effect contaminates one or both methods. Scientists continuously search for such errors, but none has been found that could explain the entire discrepancy. The most intriguing possibility is that the tension reveals genuinely new physics. Perhaps the universe evolved in ways not captured by the standard model of cosmology. Perhaps additional forces, or particles, exist that influence cosmic expansion. Finding such new physics would revolutionize our understanding of reality at the most fundamental level. What makes this especially troubling is that the Hubble constant isn't just an academic number. It reveals how the universe has evolved over its entire history. It determines the universe's age, size, and ultimate fate. Getting it wrong means misunderstanding the cosmos at the largest scales. And speaking of large scales, scientists just confirmed the existence of something that had only been theorized for decades. Dark matter makes up 85% of all matter in the universe. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. We know it exists only because of its gravitational effects on visible matter. Galaxies rotate too fast to be held together by the gravity of their stars alone. Galaxy clusters move in ways that require far more mass than we can see. The cosmic web wouldn't exist without dark matter providing the scaffolding. For decades, scientists theorized that dark matter should line the filaments connecting galaxy clusters. Mathematical models showed it clearly. Simulations demonstrated how dark matter would flow along these threads, creating channels where ordinary matter would follow. But nobody had directly observed dark matter on the filaments themselves. Until now. Researchers from Yonsei University in Seoul used the Subaru telescope in Hawaii to study the Coma cluster, a collection of over 1,000 galaxies located 321 million light-years away. They employed gravitational lensing, an effect where massive objects bend light passing nearby. When light from distant galaxies travels past a concentration of dark matter, the dark matter's gravity curves space, causing the light to follow a curved path. This creates distortions in the images of background galaxies. Their shapes appear stretched or warped. By carefully measuring these distortions, astronomers can map where dark matter concentrations exist. The team detected dark matter along the terminal segments of cosmic web filaments dangling from the Coma cluster. These terminal segments are the thin threads connecting the main filament to individual galaxies. Previous observations had seen dark matter in the main filaments and at the nodes where filaments intersect. This marked the first detection on the smallest threads of the web. This discovery confirms theoretical predictions about how the cosmic web organizes space. Dark matter doesn't just concentrate at nodes. It genuinely pervades the entire network, creating a continuous structure spanning the universe. Galaxies don't drift through empty space. They slide along dark matter highways that guide their motion. The Coma cluster itself sits on what's called the Great Wall, one of the largest structures ever discovered. The Great Wall was actually the first super-large structure identified in the universe. It's a massive sheet of galaxies, stretching across hundreds of millions of light-years. The Coma cluster represents one of the densest regions where multiple filaments converge. What makes this observation technically impressive is the difficulty of gravitational lensing measurements. The distortions are subtle. Background galaxies appear only slightly stretched. Detecting this requires extremely precise measurements of galaxy shapes, correlating those shapes across large areas of sky, and carefully removing all other sources of distortion, like atmospheric effects or telescope optics. The Subaru telescope's 8.2-meter mirror and advanced instruments made these measurements possible. The team analyzed hundreds of background galaxies, looking for systematic patterns in how their shapes were warped. The pattern revealed the gravitational influence of dark matter threading through space. This finding matters because it provides direct observational evidence for the cosmic web's most basic prediction. If dark matter exists and organizes on large scales, it must line the filaments. Now, we've seen it doing exactly that. The universe's largest structure has revealed its invisible skeleton, and that structure might be far more populated than anyone imagined. For years, astronomers estimated the universe contains approximately 200 billion galaxies. This number came from Hubble surveys that counted galaxies in small patches of sky, then extrapolated to the entire observable sphere. The calculation seemed solid. Multiple independent surveys agreed. Webb has forced a revision. The galaxy density in Webb's deep fields significantly exceeds what Hubble surveys suggested. If these deep field observations are representative of the universe as a whole, the total number of galaxies could be trillions rather than hundreds of billions. Think about what this means. Every estimate of cosmic structure, every calculation about total stellar mass, every prediction about how many stars and planets exist, All of these depend on knowing how many galaxies there are. If the true count is 10 times higher than previous estimates, everything scales up accordingly. The implication for planets is staggering. Our galaxy alone contains approximately 200 billion stars. If each star has an average of one planet, that's 200 billion planets just in the Milky Way. Multiply by 200 billion galaxies, and you get 40 quintillion planets in the observable universe. But if there are actually trillions of galaxies, the number jumps to 400 quintillion planets or more. 4, followed by 20 zeros. The scale becomes almost incomprehensible. For every grain of sand on every beach on Earth, there might be 100 planets out there in the cosmos.